Hello everyone, Steve here with a video dedicated to debugging 3D printed pendulum clocks, specifically the wall-mounted clocks that I design. And I try to make these clocks as easy as possible to put together and hope that they go together trouble-free, but there are a few steps that need to be done to make that happen. And over time, I've been asked the same questions over and over. So the assembly guide for this clock, I expanded a lot of the debug sections, and I thought it makes sense to put it into a standalone guide and this video to go along with it, because most of the features that allow this clock to operate smoothly apply to all of my other clocks as well. So follow along, there will be chapters down below, and I'll put a link to this debug guide down below so that you can download it and follow along, because some of the older manuals don't have as much detail on the debug steps. But this manual is pretty generic, and so you should be able to follow along for any of the clocks. The manual is kind of broken into sections. It starts off with printing the parts and some of the pre-assembly cleanup steps that are needed to make the clock run smoothly. There's a few gear assemblies that need to be put together, and I'll talk about a couple of those that I get asked the most questions about. Another concern is hanging the clock properly so that it doesn't sag. There's a section in here about that, and I'll explain why that's important. And then when it's all put together, some of the final steps. And at the very end, there's a section on, at the very end, there's a section on debug that starts repeating all of the pre-assembly steps to double check those. But then it goes through some, is the clock doing this? Try this. Is the clock doing this? Try this. So a couple of things to try. That actually is 2 full pages of things to try to help guide you through the steps. You can also ask questions on YouTube, on my mini factory, on my personal website. Lots of ways you can ask the questions, but follow along with this guide and maybe this will answer the questions for you. One of the first steps is printing the parts, and I show some diagrams of the gear tooth profiles that I design on the latest clocks are optimized for the Arachne slicing engine. This debug guide shows what the gear tooth profiles are supposed to look like with nice, clean, flowing lines. And then it shows some of the older gears that were designed before Arachne was available. This would be gears in some of my older clocks. So the key point to take away from this is look at the slicer and make a few changes so that you get the cleanest prints. The other thing to keep in mind is that 3D printed gears are not injection molded. What I print on my printer may be different than what you print. 3D printers may be optimized to make the outer gear profile as accurate as possible, but I believe that there's a sacrifice on the hole sizes, and especially with different filament types. Like silk PLA likes to shrink in on itself and the holes become smaller. One of the first steps is to try fitting the gears on the arbors and give them a spin. And here's a gear that hasn't been cleaned up yet. See how quickly that stops? And what is needed is a drill bit, and I like to use a small pin vise because I can control how much pressure is applied, and I really only need to go through one time with the appropriate size drill bit. And most of the gears they may be thick this way, but only the ends need to be drilled out. And there's a picture in the debug guide and in most of the manuals showing which portions need to be drilled out. Drill the holes and blow out any of the loose pieces. And now see how long that gear is going to spin? That's what you're aiming for. You want low friction. If you're going to build a clock with a runtime of 8 days, you can't have friction built up right at the beginning from the gears spinning on the arbors. That applies to the gears spinning on the arbors and the arbors spinning in the holes in the frame. So drill out the holes in the frame as well. The debug guide will walk you through a lot of the steps. So if you follow along with this guide, it'll show you what you need to do. One of the first steps is to dry fit a lot of the parts together. There are some printed parts that have to go through a printed hole, and sometimes it fits and works beautifully. Other times there's a lot of friction. Dry fit the parts that are listed in the manual that need to be checked, and make sure that they spin easily. If they don't, you can wrap some sandpaper around the shaft to reduce that diameter. You can run a file, or you can use a round file and clean out the hole. Lots of ways you can clean out the irregularities on the printed parts. You can also add some lithium grease to the arbors that pass through. You want to make sure that all of the parts that need to move past each other can move smoothly without friction. The moon phase clock has gear 6 passing through the main dial. It also has the moon phase dial that needs to rotate around gear 6, so both of those need to be checked. And then the ratchet assembly, some of the clocks have a post on gear 7A and a hole on gear 7B that helps hold these parts aligned. Those need to move smoothly. And also the ratchet clicks need to spin freely around the screws. And if you've tightened the screws too tight, back them out a little bit so that these are loose. When the ratchet goes together, you want to test that. And I've put the springs into gear 7B, and it kind of takes 3 fingers holding that together so the springs don't go flying. Put it together, and then test it. Does the ratchet click in one direction and then stop? And also, does it go all the way back to the stops? It often helps to add a small amount of grease on the sliding parts of this, just to make sure that it goes back to the end stops properly and evenly. And then there's a section in the manual to dry fit the parts to see how well they fit together, and make sure that these tapered pegs fit into the tapered holes and that part bottoms out all the way. The pegs should be doing most of the work in keeping the frame aligned. The screws are there merely to hold things together. But if the frame doesn't go together all the way, maybe there's some roughness on the pegs or on the inside of the holes, maybe some elephant's foot. Clean up whatever needs to be cleaned up so that the parts will go together with no gap. These screws don't need to be tightened super tight. Their main purpose is just to hold things together. So just tighten them till they bottom out, and that's good. There's no need to over tighten these screws, because if you have to take it apart multiple times when you're debugging the clock, you don't want the screw holes to be stripped. No need to over tighten these screws. And each clock has a slightly different procedure on assembling the frame. Follow the appropriate manual for your clock. The arbor holes in the frame need to be checked so that the arbors will go in and spin freely. If you need to drill those out, use a small pin vise. That's the easiest way to be able to drill carefully without melting the part. The last component that I get asked a lot of questions about is the friction clutch. And I think it's a fairly elegant design, but for some reason it does get a lot of questions. There's a picture in the debug guide, but follow along with the picture in your specific manual. This is the picture for the moon phase clock. Gear 4A goes over the arbor, and this arbor has a flat for the minute hand at the top end, and that needs to spin freely. And then a pen spring, there's another spacer, and then gear 4B just goes together all the way, and then a metric screw holds gear 4B on the shaft. And the way this operates, I'll show with the minute hand attached. The way this operates is, in normal operation, the large gear 4A will turn and it will move the minute hand with it. So imagine that it was in the clock like this. But if you want to change the time, gear 4A is rotating very slowly with, from the weight shell provides power to rotate gear 4A. Gear 4A rotates once per hour and also pushes the escapement. But the friction clutch allows you to move the minute hand while gear 4A is held steady. But notice gear 4B rotates with the minute hand. One of the first things to check is the bearings supporting the pendulum. Can I move the pendulum to the side, release it, and expect that there's a low enough friction on these bearings that this clock will run with a reasonable amount of drive weight? You can bring the pendulum to the side as far as it wants to go reasonably and just let it go. And then time how long it takes for the amplitude to degrade. So I'm just going to let the video run and we'll see how long this takes. The pendulum free swing test has been going for over 15 minutes now. Those bearings are definitely low enough friction to operate this clock properly. If you come to me asking for help debugging your clock, one of the first things I'm going to ask is, how long is the pendulum free swing test? So go ahead and run it. It's easiest when you have just the bare frame. Go ahead and run it. See how long the bearings will swing. The next checks are to look for end shake in a few of the critical locations, specifically the arbors that have a lot of gears stacked together, like the central arbor. On this clock, that includes gears 4A, spacers, gear 4B, I believe this one's called spacer 6, gear 6, and then gear 10, the moon phase dial. And when all of those are installed, there should be a small amount of movement left to right. If not, these gears will be pinched and that will add a lot of friction. Another thing you can check is that all of the gears spin when the frame is assembled. Normally you can test this when it's flat on the bench, but all of the gears spin when they're mounted in the clock. The moon phase clock has another arbor with a lot of gears stacked together, specifically because it has a friction clutch for the moon phase dial. So I'm checking that there's end shake on that gear stack as well. If those two locations look good, most of the others are very likely good. You can go ahead and check them if you like, but if the central arbor has some end shake, it's quite possible that all of the gears will have enough end shake for the clock to operate properly. If there was some pinching on those gear stacks, you could thin down the small spacer underneath gear 6. I mean, just look for places that you can remove a little bit of thickness. On this clock, the two notches on gear 4A and the spacer above it, those could be trimmed a little bit if needed. Normally there should be enough space, but sometimes when there's a lot of gears stacked together, if each one is a little bit taller than expected, then that adds up and closes off the designed in end shake. I've got all the gears added back into the clock, and I want to show an important step about why hanging the clock properly is important. All of my clocks have a primary beam at the very top of the clock. The back frame and the front frame hang off of that beam, and the position of the weight shell is such that maybe 60% of the weight is on the front of the clock and 40% is on the back. So this beam needs to support all of that weight without sagging. That's why I recommend printing with 4 perimeters, 25 or 30% infill. But the other important step is that the screw that the clock hangs on, that's why I brought out this board so I can show the side profile, that screw depth is very important. So I've started with the adjustable standoffs all the way on the inner position, and right now this screw is way too far out from the wall, and you can see what it's doing is it's allowing this support beam to tilt downward. And if I went ahead and adjusted these lower standoffs and then added weight, this beam is not going to bend, but the frame right here where it's thin and right here is going to bend. This whole frame will become a parallelogram, and I don't call that frame sag. I think I would call that the clock not properly supported, making it look like the frame is sagging. I'll try to pull on this without moving this piece of wood, but right now there's a gap at the top where this clock is supposed to be hanging, and that's making this top support beam tilt downward. This clock is going to be completely skewed if I try to make the clock operate like that. So it's a little bit of trial and error process, but keep going back and forth and adjusting the depth of that screw. That is a really snug fit right there. And you can see that this, if this was the wall, this beam is completely perpendicular to the wall. Right now I don't have any weight on it, but these standoffs are not trying to be tilted into the wall. Then I want to adjust the upper standoff, and that's already getting a lot firmer. Now the upper part of the clock is supported between here and here. Now I can adjust the lower standoffs. And I'm just adjusting the standoffs until they touch the wall, and then tighten the nuts to lock the standoff position. When everything is adjusted properly, you should be able to put some weight on the front of the clock and not see any movement. So I can easily add the weight and this frame is not going to sag. I don't think this beam is going to sag. If the clock is mounted properly to the wall, that beam will be held horizontal. The lower standoffs hold the clock from flexing in or out. That keeps everything vertical. And the clock can easily support the 5 kilogram or 10 or 11 pounds of drive weight. I can wind the clock, and when this clock is hung vertically, it should be reasonably close to being in beat, but you can tilt the frame to the left or the right and change the beat. And the way you can check that it's in beat is look at the overlap on the left and the right. And right now this clock is horribly out of beat. You can see there's only a tiny bit of overlap on this side and a very large amount of overlap here because the clock is tilted to the side. So bring that back until the left and the right side are relatively balanced. The rate of the clock is completely dependent on the length of the pendulum, which can be adjusted by these nuts at the bottom of the pendulum bob. And the nominal starting point is with the top of the nuts somewhere near the middle of the adjustment range. You can go up or down from there to tune in exactly how much weight your clock will need. There can be variations based on the density of your bob, the density of your rods affect the effective length. So there could be changes on your clock relative to my clock. And another thing that I've done on this clock is the middle portions of the pendulum rod are two different lengths, and it works nominally with one of the shorter ones and one of the longer ones. If it turns out that you need more adjustment than what is allowed on these adjustment screws, just print 2 of the longer ones if the clock needs to be sped up. And if the clock needs to be sped up and you've raised these nuts as high as they'll go, then print 2 of the shorter arms and just use those. And that gives you a little bit more adjustment. If you've done all of that and the clock still doesn't quite work, the last few pages in this debug guide will walk you through some of the things that you can try. Let me read a couple of them. Is the clock hanging properly to minimize frame sag? We've gone over that. Is the clock in beat? And that's tilting the clock to the left or the right to adjust the beat. And even when you wind the clock, you might have tilted it. You may want to check the beat to make sure the clock is still in beat after winding. Does the escapement rotate quickly? And you can see on this one, let me move the pendulum slowly. As soon as the pallet clears the escapement, notice how energetic that escapement is. If this escapement is sluggish, and typical reasons for it to be sluggish are not enough drive weight, too much friction somewhere, I'm going to try to simulate extra friction somewhere. So notice how slow the escapement is. It just has no energy. So the pendulum is swinging, and I know this pendulum will swing for 15 minutes before stopping. So if the clock is stopping in a minute, why isn't the escapement adding any energy into the pallet which pushes the pendulum? And that's too much friction somewhere. I can't tell you where, because it might be a blob on one of your gears. It might be not enough end shake. Now, there's lots of reasons why you may have too much friction. You have to debug that on your clock. Does the pendulum amplitude just slowly degrade even though the clock appears to be running? That might be a problem of just not enough drive weight. So try increasing the drive weight. A simple thing to do is to just take a paper clip and hook it over the loop on the drive weight. In this configuration, where if this is an 8-pound weight, normally 4 pounds would be powering the clock and 4 pounds would be just hanging over here on this hook. Now I've got the entire 8 pounds powering the escapement. Is the escapement energetic now? That's telling me that I needed a little bit more drive weight, or I need to find out where the excess friction is. Does the pendulum stop swinging in less than a minute? If the pendulum was free swinging for 15 minutes or more, why would the clock stop running in less than a minute unless the escapement was somehow interfering and actually getting in the way of the pallet and stopping the motion of the pendulum faster than the normal decay? The next question could be, what is the pendulum amplitude? And there are swing gauges that you can print and put down at the bottom of the pendulum and then measure the amplitude. They're graduated in full degrees and 0.2 degree steps. The clock typically needs about 1 degree to the left and 1 degree to the right in order to continue operating. But it's nice to see more than that. I like to see about 2 degrees in each direction. That's telling you that you have a good drive weight. The next concern is, does the clock appear to run, but the time does not change? That typically goes back to the friction clutch. Is there some end shake on the central arbor? And you can check that by pushing and pulling on the minute hand. That's telling you if there's end shake on that gear stack. Or do you need to stretch the spring in the friction clutch? There's a few things you can do to make sure that the friction in the friction clutch is stronger than the friction in the gears. And there should be very little friction in the gears. So it doesn't take a lot, but if, you know, you can double check the assembly of the friction clutch. The next thing to check is look at the clock from the side. Now I'll just rotate it here. And are there any gears that the sidewalls of the gears are touching where they're not supposed to? There's a few that come close. If the frame is sagging or tilted, that's going to exaggerate some of those gears wanting to touch. But just look down the side of the clock to see if there's anything touching that isn't supposed to touch. And if all of those checks fail, look for excess friction. You may need to take the whole clock apart, put it on the bench, and then test one gear at a time. Does it spin in the frame? Then test 2 gears at a time. Maybe start with gear 4. Does that, gear 4 and gear 3, do those spin easily? Add gear 2. Put the frame back on so that the arbors are lined up. Are they still spinning easily? Add the escapement. Add gears 1 by 1. Test them in pairs and make sure that they continue to spin with minimal friction. Another thing you can try when you're debugging the clock, if all of those other steps don't work, you can try just running the clock without the pallet, and you should be able to start and stop the escapement at any time, and it should start right back up again. And start it from multiple positions as if the clock was operating, and then just let it run. Maybe that'll break in some of the components. I'm running with the full-size weight shell, and it might take an hour for this weight shell to hit the floor, but just let it run. If the clock stops for some reason, like, you know, if you see that the gears are sluggish at any one spot, start looking for friction. Maybe there's some binding right where the right where the gears stop. So just let it run. Then do this a couple of times. Maybe it'll break in a couple of the components. Another thing you can try is adding lithium grease to the pinion teeth. You don't need to add grease to the outer gears because the grease will work its way into the outer gears. But just a very tiny amount of grease with a toothpick, and then let the clock run. You should be able to wipe off most of the grease, but it'll still have an effect. Make sure that you've tested the pendulum bearings and make sure that those are low friction. So there's lots of ideas in this debug guide. If you have other questions, you can message me at the various locations. That would include my website forum, my mini factory messaging, comments to this video, lots of places you can get a hold of me. I'll try to answer your questions and help you get the clock running. So thanks for watching, and hopefully this was helpful if you have issues getting your clock running. Thanks a lot. Bye.